Welcome all of you. In the last class, we started discussing about nuclear overhauser effect. I told you in the case of NOE, first it was predicted by Overhauser. He showed that by irradiating electron spins, we can enhance the polarization of the nuclear spin by nearly 1000 times. 1000-fold enhancement in the signal intensity was seen without changing the magnetic field. So, that was the first thing. It was called dynamic nuclear polarization. Subsequently, it was also shown this phenomenon is possible even between two nuclear spins also. So, what is nuclear overhauser effect? We understood certain conditions, certain restrictions for that, what are the requirements for that. These are when you decouple a particular spin or irradiate a particular spin with certain RF power, 2 or 3 things can happen. Either when you decouple that particular peak, the peak which is coupled to it can collapse it into a multiplicity, can collapse into a singulator simplified pattern, or it can so happen it can change the intensity. The change in the intensity could be either positive or negative. And also I said for such a phenomenon, the 2 nuclear spins need not be J coupled. What is required is what is required is spatial proximity between 2 nuclear spins. The spins have to be close in space. So, and the NOE phenomena depends upon various factors. I discussed about spectral density function, correlation time, everything. And we started discussing about an example of 2 spins which are uncoupled kept in a magnetic field. Immediately after putting in a magnetic field, there is a saturation state. All the spins are saturated in such a way there is no population at all, no population difference at all. Finally, what happens? Wait for some time, the spin systems attain thermal equilibrium and there is redistribution of spin populations. And for the 2 spins which were kept in the magnetic field, which are close in space, we found out that the intensities are equal. For 2 transitions for each of the spins, intensities were identical. We just for the calculation purpose, we call it as 2:2:2:2. And then what we did is we irradiated one of the transitions or one of the spins with a low RF for a long time, and then saturate that particular spin, and then measure the intensity of the other spin which is close to it. We found out again there is no change in the intensity, and after certain time spins will come back, revert back to thermal equilibrium. It attains thermal equilibrium. This is what we observed. So, then the question is, just by irradiation alone we found this intensity of the other spin which is close in space will not change. So, NOE phenomena cannot happen just by irradiation of one of the spins. Then what is that which is responsible to bring in NOE phenomenon? What I said was we have to consider some of the relaxation pathways. We also worked out what are the transmission probability for single quantum, double quantum and 0 quantum also we discussed. But now I said these transitions are disallowed, 0 quantum and double quantum, other than single quantum, other transitions are not allowed as per the selection rules of NMR. But however, in the context of relaxation, they are allowed. So, with this idea, now we will bring in another term called cross relaxation. Instead of spins attaining thermal equilibrium by undergoing transition among the single quantum transitions, what happens if we allow the spins to adopt a different relaxation pathways? For example, the spins can relax through double quantum pathway or it can relax through single quantum pathway, either of them we can do. Let us see if that pathway is adapted for the spins, will there be any change in the intensity. So, we will start with that now and see what is going to happen. So, this is what is going to happen, this is what it is. Now, we will introduce cross relaxation. It is a relaxation that occurs between the 2 spins via dipole-dipole interaction. Of course, this is a dominant relaxation pathway we have been discussing even from the relaxation phenomena which we introduced. Now, we will consider the situation. In the presence of irradiation of one spin, for example A spin, the transition probabilities can have various effects. We will consider like this. If WA1 single quantum, if you consider, if you irradiate A spin, there is no effect because A spins are being irradiated. If A spins are irradiated, you will not see any effect. On the other hand, we observed that no effect is seen because S transition is already at equilibrium. So, there are two possibilities we can think of, probabilities. They have different effects. When I irradiate one of the spins, remember, when I irradiate A spin, it has no effect because it is in a saturated condition, saturated state, and W1S is already at equilibrium, no effect. But now, let the system relax in the presence of an irradiation field in a different pathway. We can think of two possibilities. I told you alpha alpha to beta beta relaxation we can think of, or beta alpha to alpha beta relaxation we can think of, either of them. Here two spins are changing their states simultaneously, it is called double quantum. Here again two spins are changing states simultaneously, but it is beta alpha to alpha beta or alpha beta to beta alpha. It is a 0 quantum transition because the magnetic quantum number here is 0. So, 0 to 0 transition, it is 0 quantum. On the other hand, it is plus 1 to minus 1, change is plus or minus 2, it is called double quantum transition. Okay, either of them we can think of 0 quantum. Let us see what happens if I do this. If this can happen, there could be redistribution of spin population to achieve a new equilibrium. Earlier we saw one type of equilibrium when the spins relax through single quantum pathway. Now let us see with this whether there is any redistribution of spin population which is different from what we observed. Let us see that. Now we have already irradiated the spin, okay, spins, this is the spin population. Now we have saturated A transitions, you see A transitions of equal intensity already done. So, A spins have been saturated. Now, let us see X transitions. By allowing the spins instead of attaining thermal equilibrium by these pathways, why not we allow it to come down directly through double quantum pathway and see what is the change we are going to see. Okay, let us see that now. Now, spins will jump from beta beta state to alpha alpha state. It is a double quantum transition. It is relaxing through double quantum pathway. Now, let us recalculate the population difference for X transitions. Of course, A transition if you consider, now it is 1 minus 0, it is 1. Similarly, here A transition if you consider 4 minus 3, it is 1. So, A transition has reduced in intensity by half after the spins relax through double quantum pathway. That is not interesting because we are irradiating that. Let us see the effect of this on the neighboring spin X. What is happening to that? Recalculate the populations of spin X now, population difference. This X1 transition is now 4 minus 1, it is 3. Similarly, X2 transition is 3 minus 0, that is also 3. What was our population difference when we started with equilibrium and after irradiating we saw population difference was continuing to be 2 2 2 2 only, there was no change. But now you see there is 50% enhancement in the intensity. We did not do anything, we only assume that spins are relaxing through double quantum pathway. So, by irradiation of A spin, we saw enormous change in the intensity of the other spin which is close in space with it. So, there is a 50% rise. This is what we are going to do. This came down by 50%, we are not interested in that, whereas X has gained in intensity by 50%. This is called a situation of positive NOE. Remember, positive NOE. So, what do we understand from that? If the spins adapts or follows the double quantum relaxation pathway, then we can see positive NOE. There is a change in the intensity of the signal. All right, this is a positive NOE case. Now, let us continue to do the low power irradiation for some time. We will not get, all these phenomena are happening while we are irradiating one of the spins continuously with low power RF. Now, after some time what will happen? Wait for some time T1, which is the relaxation time required for the spins to come back to Z axis, attaining thermal equilibrium. Now, it has come to this state. This is where we started with. After attaining thermal equilibrium, this was the spin population we took for calculation of intensity as some numbers. So, again 4, 2, 2, 0 it came. Now, we recalculate the populations. Population difference if we recalculate, now it is again x is 2, a is 2, 2, 2. So, intensity has come to the original state. That's why that's one way. So, this is possible. Now, we can think of another thing. Let the spins relax through zero quantum pathway. Why I should go through double quantum always? There is no need for it. It can adopt zero quantum pathway also. Let us see if the spins relax like this. One of the spins relax like this after irradiation for a long time, for some time. Now, recalculate the population difference. Look at it, A transition again, 2 minus 1 is 1, 3 minus 2, A transition always continue to be half, that has not changed. In the double quantum relaxation pathway also it was half, reduced by half, now also it is same. What about the X transitions? Look at the X transition here, this is 3 minus 2, it became 1. Here 2 minus 1, it became 1. We started the 2:2 intensity. Now, with a zero quantum pathway, we came it to 1:1 intensity. What is the change you observed? There is a reduction in the intensity of the signal. In fact, the X transition came down by 50% loss, 50% reduced intensity. This is called a case of negative NOE. Okay? So, now we understood. You can just by irradiating the spin, allowing them to relax the single quantum pathway will not give rise to change in the intensity of the spin which is close in space with that one, with the irradiated spin. On the other hand, if we allow the spins, or let us say the spins follow cross relaxation, it can follow double quantum relaxation pathway or zero quantum relaxation pathway, either of them, both of them it can follow. It is a competitive process, we do not know, it need not follow only one, it can have both the paths, which is dominant is important. If it adapts the double quantum pathway, we say positive NOE. If it adapts zero quantum pathway, we have a case of negative NOE. So, now we understood, even by irradiating RF power, we are not doing anything, only thing we brought in cross relaxation phenomena where spins are allowed to relax through double quantum and zero quantum pathways. Okay. Now, continue to irradiate with low power RF. What is going to happen? System will come back to original equilibrium. New equilibrium is attained. That new equilibrium is what we started with after putting the sample in a magnetic field. So, that means the same 4, 2, 2, 2, 2 intensity. So, in between when you are irradiating, this phenomena can happen. Change in intensity, case of positive and negative NOE can happen. Now, let us understand one thing, W1 transition probability, that is single quantum transition probability, do not create NOE. If this is the dominant relaxation pathway or this is the most efficient relaxation pathway, then NOE may not develop at all. You will not see NOE if W1 is a relaxation pathway, dominant relaxation pathway. On the other hand, if W2 is an efficient pathway for relaxation, then for like this you can observe this phenomena can be experienced in small molecules where there is fast motion and the motional frequencies are very large, then W2 is an efficient pathway for relaxation and you get positive NOE. So, you understand A positive NOE case, there should be a double quantum relaxation pathway, W should be more efficient, and this can happen for small molecules undergoing fast motion. So, W0 if you come, if that is the efficient pathway for relaxation, that is for 0 quantum, this can obviously happen only for large molecules. Large molecules undergo slow motion and frequency distribution is small frequencies, not large frequencies. W0 is very small, in which case the dominant thing is negative NOE phenomenon. So, positive NOE, negative NOE, now you understood, it is depending upon the relaxation pathway and also on the size of the molecule and depends upon molecular motion. Small molecules you have positive NOE, W to the relaxation pathway, large molecule negative NOE and W0 is the relaxation pathway. But remember, these are not exclusive processes. I told you both W2 and W0 are competitive processes. It can be happening simultaneously. You cannot dictate terms of the nuclear spins to follow one particular pathway. So, it is a natural phenomena, both can happen simultaneously, and also W1 can also be happening. All the 3 relaxations pathways can be adopted by the nuclear spins simultaneously, and which is dominant relaxation pathway defines whether you have positive NOE, negative NOE or 0 NOE or no NOE at all. So, that are the things we have to understand. So, this is what you should know. NOE positive, negative or 0 is dominant relaxation pathway is one dictated. So, in summary, when W2 is very much greater than W0, then NOE is positive. If W0 is very much greater than W2, NOE will be negative. If W2 is approximately equal to W0, not exactly, approximately, which you can always write, there is no NOE. This is the basic rule you must remember. What will happen when W2 is very much larger than 0, that is dominant, NOE is positive. If W0 is dominant, NOE is negative. When W2 equal approximately equal to W0, there is no NOE at all. Okay. Now, saturating the transitions for a period of time that is long related to the relaxation times, where the spin system attain new thermal equilibrium, new steady state, that is attain steady state population. It is because of these competitive processes. Eventually, the change in the intensity when you measure, this is what is happening. We are irradiating for a short period of time, relatively long compared to relaxation times, and the spins will attain new steady state and change in the population, whatever it is, we are going to observe while it is happening because of competitive processes. And this is what eventually we are going to measure. So, since the spins attain steady state because of this low power irradiation saturating the transition for a short period of time, this is called steady state NOE. This is called steady state nuclear over-Hazer effect. Okay. The gain in the intensity, you may ask me, okay, there was a change in the intensity, positive or negative, that is what we observed because of relaxation pathways. How much is the gain? How much is the enhancement in the intensity or reduction in the intensity? Can we work it out? Of course, you can work it out also. Detailed discussion can be given, detailed mathematically you can work it out. But without going into that, I will give you, there is a qualitative treatment for this phenomena. This is an equation given by Solomon called Solomon equation. What is the Solomon equation? It is this one. This is Solomon equation, which says the change of the intensity with respect to the thermal magnetization. If you find out, this is given by the simple expression W2 minus W0 over 2 times W1 into plus W2 plus W0, and it is also multiplied by gyromagnetic ratio of the spins which you are irradiating and the spins in which you are observing the change in intensity. These two are important. Gyromagnetic ratio is important and W2, W0 and W1, all the 3 are important. And then if you know this, you will know what is the change in the intensity. This is a qualitative treatment for Solomon equation. Without deriving, I am giving you this. And this is what is important parameter to be observed. Now, in this thing which is highlighted, in the numerator you see W2 minus W1. This term is called cross relaxation. It is called sigma is called cross relaxation. It is a difference between double quantum and zero quantum transition probability. So, W2 minus W0 is called sigma is cross relaxation between spin I and S. Whereas the denominator you saw W1x plus W2 plus W0, this is the longitudinal dipolar relaxation. This is what is this one? This is not cross relaxation. This is longitudinal dipolar relaxation rho is. This comes in the denominator. Now, what are the rates of W2, W1, W0 processes? We discussed this not with respect to this in the T1 measurement and relaxation. When we discussed the concept, we knew for dipolar interaction, dipolar relaxation, there are processes which gives rise to certain frequencies which aids in spin system to give its energy to the lattice through dipolar interaction. And we found out and we discussed that they are called spectral density functions J omega. You remember that? We discussed that it is a spectral density function J omega. So, J omega, the spectral density function, depends on the motion of the spins and also on the Larmor frequency. We knew this, we discussed this. J omega, and we also found out it depends upon both molecular motions and Larmor frequency. That is, we in turn we discussed about tau c and also omega 0. It depends upon both of them. Okay. So, let us consider we are recording the spectrum at 400 megahertz, which is the resonating frequency for protons. Then what are W1, W2 and W0s? W1, the spectral density function is approximately equal to 400 megahertz. That is what is said. It is a resonating frequency of the, it is nothing but the Larmor frequency of omega 0. W2, JW is double the Larmor frequency, it is 2 omega 0. Whereas W0 is the difference in the chemical sheet, very small difference. Okay. So, this is of the order of few kilohertz. This is megahertz, since it is 2 omega, twice the Larmor frequency. If you are working at 400 megahertz, this is 800 and this is 400. You understood how the spectral density function depend upon the Larmor frequency. Of course, further we also know it depends upon tau c. Later we will of course we discuss, maybe if there is possibility we can touch upon it. So, JW gives distribution of the frequency of oscillations, oscillating dipolar interaction over a wide range. Okay. And for small molecules in low viscosity solvents, molecular motion is faster than Larmor frequency. That is, W2 is dominant than W0. Double quantum relaxation pathway is the efficient relaxation pathway. So, we are going to get NOE, which is positive. Remember, when the molecular motions are faster than nu 0, we will talk about W2, which is twice the Larmor frequency. Then there is a case of positive NOE you are going to see. For such solution, the relationship for W2, W1, W0 has already been worked out. We don't need to discuss this in depth. It is nothing but 12:3:2. That is the relationship for small molecules undergoing molecular motions at faster than Larmor frequency. So, for homonuclear case we will consider, plug in these numbers. What is gamma A, gamma X is same for homonuclear case, and then put into that equation and find out. You will see that there is a 50% enhancement, maximum gain you can see for homonuclear case. If you take proton, for example, proton NOE, maximum gain you are going to see because of NOE is only 50%. That is what you are seeing. Okay. Of course, now you may ask me a question. We are dealing with two spins. What happens if there are more number of spins are there in the space which are close by? If all of them can also give rise to NOE. For example, I have 3 spins. I am irradiating this spin. I looked at the intensity of this proton, change in the intensity. I said in the homonuclear case maximum is 50%. Then what about this spin? If it also can get affected, can it not give intensity for that together? Will it not be enhanced? Enhancement will it not be much more than 50%? No. Please remember, even when a single proton experiences NOE from several other protons, the sum of all the NOE enhancement together for a single proton cannot exceed more than 50%. That is the maximum enhancement you can get. Whether the proton experiences or get the NOE from one proton or 2 spin effect, 3 spin effect, no problem. The total NOE sum of all the from all the other protons, the total NOE if you calculate, it can never exceed 50%. Take for example a situation like this. I am looking at the proton A. This proton 4 can give NOE to it, proton 3 can give, proton 1 can give, proton 2 can give simultaneously. In which case I will call it as, let us say, NOE 1, 2, 3 and 4. 4 things we get. This is photon 1 gives NOE 1, this is 3, this is NOE 4, this is NOE 2. All are possible, let us say. In which case the NOE what you are going to see at the site of the proton A is sum of NOE 1, NOE 2, NOE 3 and NOE 4. All these things together cannot exceed 50%. Please remember, if a single proton experiences NOE from several other protons, the sum of the NOE enhancement all put together cannot exceed more than 50%. That is an important point. Now, will it be same for all the molecules? Whether NOE enhancement is 50% is for all the molecules, again depends upon various other conditions. For large molecules or the molecules in the viscous solutions where the mobility is reduced or restricted, W0 is larger than W2 and W1, in which case NOE is -1 and W0 is much larger than W2 and W1, NOE is -1. Okay. So, of course, we discussed about the origin of the fluctuating fields in the context of relaxation, and of course, in the solution the motion is the rotation of the molecule, that is a dominant fluctuating field for dipolar interactions. We observed that when the two spins which are treated as a dipole, their orientation with respect to magnetic field do not change. When they undergo motion, mobility, when they undergo motion, tumbling motion, one spin keeps on rotating, let us say, it changes the dipolar field at the side of the other spin. As a consequence, the fluctuating field produces frequencies at the Larmor frequency. The frequencies at the Larmor frequency giving rise to or enabling the spins to give us energy to the lattice. So, we know that the fluctuating field generates magnetic field, and in the external magnetic field, this is because of the rotation or some disturbance of the molecule like this. Now, these fluctuating fields are the pathway for the system to release energy. We discussed this in the relaxation phenomena. So, this is needed. If there is no fluctuating field, spins cannot relax. It will take enormous amount of time to come to thermal equilibrium. So, there will be always natural fluctuating fields at some places. So, the spins eventually will come to thermal equilibrium by releasing energy. It could be seconds, millisecond, microsecond, hours or days, but finally it will achieve thermal equilibrium by releasing energy. So, thermal equilibrium has to be attained by releasing energy. So, all these things depends upon rotation correlation time we also discussed, and that tells you about the motion of the molecule. We also thought, we knew tau c depends upon the size of the molecule, that is on the molecular weight of the molecule. Okay. Tau c correlates the orientation of the molecule at two different times and depends upon several factors. We also defined tau c, it is the motion of the molecule by 1 radian, how much time, the time taken for the molecule to undergo rotation by 1 radian, that we observed, we discussed that. So, there are several factors responsible for this, for the tau c. Major contribution is from the molecular weight, that is the responsible for that. Major responsible factor is molecular weight. Basically, what is tau c is going to tell you? It tells you about the sluggishness of the molecule, how fast or sluggish the molecule is. For example, a short tau c means that the random rotation, that is small molecules, they undergo very fast rotation. Long tau c means molecule is sluggish, it is a very big molecule. For example, this could be small organic molecules, small molecules which can undergo rotation fast, undergo motion faster. This could be a very big biomolecule, that is a big protein or a big nucleotide or a big polysaccharide, they undergo sluggish motions. Okay. So, this is this pictorially you can see small molecules tumble more quickly and these are the big molecules that tumble more slowly. So, the tau c defines the sluggishness of the molecule and how fast tau c is the long or short defined by, it is decided by the size of the molecule. Okay. So, one rule of thumb for calculation the rotational correlation time approximately, I mean it is not that it should always be true. For a spherical macromolecule, if I consider more or less spherical globular molecule which is isotropic, undergoing isotropic reorientation. Isotropic means uniformly it is changing all directions. At I say at 300 K I am looking at the temperature also, then tau c is approximately equal to 0.60 times 0.6 times molecular weight. This is a rule of thumb to calculate what is the tau c. If I know the molecular weight, I know approximately what is the tau c. So, for a small molecule protein with a molecular weight of let us say 3.3 kilodalton, tau c is approximately 2 nanosecond. What is 2 nanoseconds? It corresponds to 500 megahertz. You understand now how the molecular motion and tau c decides. See, now with this you know what is JW, you know what is relaxation pathway and you know whether it is positive NOE or negative NOE. So, all these parameters are related to each other. So, motion with higher frequency will be absent for such a perfectly rigid molecule. Okay. So, now I think we will discuss more about the spectral density function and few other things related to NOE. Since the time is up, we will come back and discuss again in the next class. But right now in this class we understood a lot. We discussed about how the relaxation pathways will enable spins to gain have a positive NOE or negative NOE. We saw that for a double quantum pathway, if it is dominant, NOE is positive, and if the zero quantum pathway is dominant, NOE is negative, and positive NOE in the case we also found out it is 50% enhancement will be there for homonuclear spin systems, and for large molecules biomolecules the negative NOE is -1, is 100% reduction in the intensity, and all this W2, W0, the relaxation probability that the molecules undergo transitions and the relaxation pathway, they are all competitive processes. None of them are exclusive. All these things can happen simultaneously. So, in a molecule W1 may be there, transition probability is 0 single quantum, W0 transition probability 0 quantum, and W2 transition probability double quantum. All competitive things can be going on. If W1 is dominant, no NOE is seen at all. If W2 is the dominant, positive NOE. If W0 is dominant, negative NOE. All these things can happen, and we understood what is the rule of thumb, what is the spectral density function which is dominant, what are the fluctuating fields, how they are related to tau c. Tau c depends again on the molecule. Tau c basically defines you the sluggishness of the molecule. All those things we discussed. So, we will discuss further continuing with this NOE maybe in the next class a little bit, and then we will go to a different topic. So, I am going to stop here. We will meet again in the next class. Thank you.